So that sensitivity should be there in all of us, so that we can look around us and see where we can start using it. Yeah. And where we can start using it, we should try and use it, because it's not all that tough here. So the idea was to try and demystify it so that it starts becoming accessible to everybody. So that is the basic goal on this. Yeah. So what we will do is, let me show the topics first. Yeah. So looks a little intimidating here right now, but as we go through, the idea is to try and make it as simple as possible to understand. So we'll cover some basic items about artificial intelligence, machine learning, deep learning, something about the way the field has evolved. Then what we have done is that we will take a example which is there as a part of the entire exercise, is a mask detector. And I chose this specific item basically because one could have taken a specific domain and talked about, say, agriculture, application in agriculture or medicine or some other field. But I took this because it is field, it touches everybody's life today because of the COVID. All of us are now forced to wear a mask. And it's a common topic of interest for everyone. So the ability to be able to detect whether a person is wearing a mask or not by looking at his picture was a simple example that I used here to demonstrate what it can do. And that is what we will be going through in this entire exercise. So there is a very simple view of the problem definition and how we are going to tackle it in this particular slide here.
The meeting is recording. Joining, you are giving consent to meeting to be recorded.
Sorry, is there a question for anyone? Okay. We'll then cover a little basics of neural networks, deep neural networks, and convolution neural networks, which is one of the core technologies that we are going to use today. A little idea about what is transfer learning. Then we will go through some of the tools that have been used as a part of the solution to this problem that we discussed about face mask. The tools that we are going to talk about are Google Collaboratory. We'll talk about Python a little bit. We'll talk about TensorFlow. We'll talk about Keras. And then we'll do a bit of a code walkthrough on the mask detector code. And the final item in the list is to actually run the code and see how it works here. So this is the sequence we are going to follow. And I'm going to go straight now into the topic here. So there is a lot of confusion about what is deep learning, what is machine learning, what is artificial intelligence. So this slide basically illustrates the fact that artificial intelligence is the superset of the entire thing, and a lot of things come into this particular domain, whereas machine learning is a very specific part of that, which is about the ability of algorithms to be designed in such a manner that they can learn without being explicitly programmed here. And please note this particular point because it's very important, because it is also changing the way the software industry has started working already and is expected to move in the future, because the whole paradigm of programming is expected to change as we go along here. Programs don't need to be explicitly designed anymore, and they can start becoming algorithms which can actually learn on their own. So this is the domain of machine learning. And within machine learning, the subject which is the really hot topic right now is deep learning, which is basically the entire field of neural networks here. So neural networks have been extremely successful in solving a fairly wide range of problems. And that is why, while machine learning has many other subsets in it, but deep learning is the one which has really taken off there. And in the next couple of slides, we'll try and see how this deep learning space has evolved over the last 20, 30 odd years and where we are today in this. Okay, a quick comment. I mentioned to you that the whole paradigm of programming and software development itself is changing. And if you Google the net, you will find that this is a phrase which has become very popular now. that Mark Anderson, who was the founder of Netscape and is currently a very well-known venture capitalist, had about 10 odd years back, he had coined this phrase that software is eating the world. But the AI guys have turned it around and started saying that the AI is now going to eat software. So I was listening to a talk by Andrej Karpathy, who is today the head of the AI program at Tesla. And he made an interesting observation that 30% of their developers now are today working, their workflow is completely dominated by AI.
AI is eating software.
AI is eating software.
Artificial
Right?
intelligence is eating software.
Yes. Is that a comment? Okay. So the idea was to sort of sensitize everyone to the fact that the whole discipline of software development itself is undergoing a transformation because of AI. And we'll probably see that as we go along, and you'll experience it yourself as we try and solve this problem of face mask here. Okay, this slide is courtesy Abhay. Abhay, you're there on the call, I'm assuming, right?
Hi, sir. Yes, I'm here.
Yeah, so Abhay gave me some interesting feedback on, I checked with him that as a non-technical person, would the presentation formats make sense to you? And he said that you are talking too much about code and very little about application. So Abhay, this is courtesy your feedback here. So I'm going to spend 2 or 3 minutes on the application areas for AI and how people can start actually using it in the things that are sort of there, which are in their domain. And while AI has a very large number of applications in very diverse disciplines and domains, I have touched here only those in which I have tried to dabble myself a little bit here. So agriculture being my favorite subject in any case, I'm happy to tell you, and there are many people in this group here today who are involved with agriculture, that one of the interesting application areas in agriculture is detection of plant diseases. So if a farmer were to take a photograph of let's say tomato crop in his field, and if there is some disease, that say fungal infection on the leaves, etc., they call it late blight, early blight, etc. So if he were to find out as to what kind of infection his plant is having and what is the cure for that, he can simply forward that picture to through an app, and the AI can have a look at it and try and give you some feedback on what the problem is, what possible solutions could be there. So I tested a very similar approach to what we are going to see today in the face mask detection, and on early blight detection in tomato, and on a data set that I was able to get hold of, and I found interesting results here. So plant disease detection is a big subject. I think in India we specifically need to work on that, and I think part of the problem is that we don't have enough data sets in the public domain on which people can work. So this is an interesting application area. There are many other areas, applications in agriculture which we can discuss, but that will need a specialized discussion. I don't want to confuse digress in this particular forum. Just want to mention that agriculture is a very important domain in which AI can be applied. Then healthcare, I try to dabble in TB detection. TB, as you know, in India is the largest burden of TB in the world is in India. In fact, TB is considered to be a much bigger threat in terms of deaths per year as compared to even COVID. COVID is nowhere close to TB as far as India is concerned. So one of the interesting use cases for TB detection is that you can take a chest X-ray, feed it to the AI, and the AI can give a response back saying that what is the possibility of this particular X-ray having this patient having a TB infection. So there is unfortunately again in India the data sets are I couldn't find any public data set in India on TB whereas we have the highest burden in the world here. But the Chinese have published some data set, and I try to test a very similar approach to what we are going to be discussing today. And I found some very interesting results again. So healthcare, anyway, there are very large number of multiple applications which are possible. And a lot of work is drug discovery, patient survival rates, etc., etc. There are a lot of application areas that people are working on very intensely right now. Media and entertainment is another very interesting application area, and I was very fascinated by by having an opportunity to have an interesting discussion with Subhash Ghai, who's the Hollywood doyen for filmmaking. And with he and his team, he set up an institute in Bombay, which is known as Whistling Woods. Those in Bombay, I'm sure, would be aware of that. And we had a discussion about how Netflix has actually built an industrial scale AI workflow in their entire organization, and how in India being a very large Bollywood being a very extremely large industry and a lot of media and entertainment business in India. So they can benefit from this in a big way. And he was very keen to start a course in AI for media and entertainment in Bombay. And he said that, why don't you help us design a curriculum? But I said, I'm not a domain expert in this, and I really don't think I'm up to the task here. But in any case, I did have a look at Netflix, and very interesting application I want to share with everyone, which hopefully somebody should be able to pick it up and work on that. Yeah. So they do subtitling, as you know, in Netflix on all the in any language that you can ask for. And the subtitling, you have to be very careful that you don't place the subtitle on the face of the actor, for example. So you need to find a place which is sort of not going to take away the essence of that particular speech frame. And that they use AI it's a completely AI driven process where they use AI to find out which space is sort of empty, relatively empty, and place the subtitle in that. Yeah. Just an example. Yeah. So it's a very, very interesting way in which the Netflix has actually deployed AI on a very large scale there. In fact, the IT department there simply runs the AI backend. And the actual AI modeling and deployment is actually done by the user departments themselves. So this is what we mean by industrial scale IT AI deployment in an organization. And this is the way forward, I guess, for most industries in which data and AI applications can be big business possibilities. But this is dedicated to you, the predictive maintenance here. SR Bhatt. So you spend your life managing large plants, and I was very fascinated to see that NASA has actually published a data set and a public challenge for gas turbines here. So what they have done is that they have taken about 21 odd parameters from sensors, temperature, flow, etc. for gas turbines. And over the life of the gas turbine, they have published the data set as a time series here. So if you can do a multivariate analysis of that time series of data from the engine, you can actually try and determine how close the engine gas turbine is to failure, based on their historical experience here. So this is a very interesting problem area in which I believe a lot of work needs to be done. Although it is complete, the approach for here, time series approach, is very different from what we are going to be discussing today. But this is a topic for more work and discussion as we go along here. Then another time series based problem for AI is the power demand prediction. So as you know that the power utility at DISCOM today has to buy power from various generation sources, and today because of fairly open market conditions, they can buy from renewable, non-renewable, and they have a choice of vendors from which they can procure, they can have a power purchase agreement there. But if they end up defaulting, if they have said, I want to buy 100 kilowatt hours, 100 megawatt hours, and they actually end up buying because the demand was actually less than they predicted, or they ended up buying more, using more than what they had asked for, they have to pay heavy penalties. So there's a very strong need for them to have as close as possible a demand prediction for power, so that their financial this thing is not affected. And this is a time series again, time series problem. And of course, you can use the ARIMA model to do this time series prediction, which is fairly simple. But if you want to do multivariate, then AI models, neural network models are a better bet, especially RNN and LSTM, which we are not going to cover today, but that's a topic for another day. So this is one area which I've been dabbling a little bit, and I'll be happy to discuss with someone if he is interested in this later. In the business side, in our HR and marketing, one simple use case which is sort of out there in the public domain, and a lot of data sets are floating around, is about churn. So HR, they use it in the sense that if if you look at data characteristics and the historical data of HR, you can see patterns of when an employee is likely to leave. Yeah, but certain signals you can get from his data set that he is likely to leave. So the HR can then start planning in advance that, okay, these people are there is going to be likely to attrition in this particular area. They can start planning for that. The same thing in marketing, exactly the same thing, that if you look at the customer data set, you can get signals from an AI model as to when a particular customer is likely to churn, and then you can try and take corrective actions if you wish to do so. Yeah. So these are some examples which are data sets are publicly available in all the cases that I discussed right now. The big thing is the data availability. If it is there in the public domain, then it's possible to work on them. If there's no data available, it's very tough to do anything here. So here are some use cases that I've mentioned here, and we happy to discuss with anyone if there is specific interest in some of these areas. Okay, any quick comments or questions before we launch into the next set of slides here? All right, I'm assuming that we are good so far. So let's move to the next one. This is a very interesting slide. So this shows several things, and I'm sure that a background of how a field evolves is very interesting always, and hope you enjoy this. Yeah. So while AI has been around for multiple decades, but the deep learning domain, which we discussed in the beginning by saying that deep learning is a neural network, which have become extremely powerful and popular today. The credit goes to Geoffrey Hinton in Canada, who's a professor at University of Toronto. And he and his team, in 1986, they proposed the whole concept of backpropagation. While neural networks is a conceptual idea, has been around even long before that. But there was always a problem in terms of the mathematics to solve the problem of training a neural network here. The concept has been there for long. So Geoffrey Hinton developed the maths behind which is known as backpropagation, where you take a training data set and you have labels saying what the outcome is expected. The network goes through a certain process, finds out the result that it is able to predict, it matches it with the result that was expected to be there, and then it backpropagates and adjusts all its parameters to sort of upgrade itself to be able to do a better prediction here. So the maths behind all this is credited to Geoffrey Hinton, who's considered as one of the godfathers of deep learning here. So his student, Jan LeCun, who's also a legend, and he's currently the head of AI at Facebook. And please see the slow pace at which it is moving now. So 3 years, he was a student, so he knew exactly what Geoffrey Hinton was doing here. So he took 3 years after Geoffrey Hinton did the backpropagation maths to actually come up with a practical application of the entire thing. So the problem he cracked was the zip code recognition, 3-layer neural network, very simple neural network for zip code recognition. So you had handwritten digits. You see, the postal department always had a problem of when people would write letters, they would put the zip code in the end, and they wanted an automatic way to read the zip code here. That the person who sent the sender of the letter is written in his handwriting here. So handwritten code recognition of handwritten characters, numeral digits, was a problem that Lee Yakun worked on, and he was able to show that a simple 3-layer neural network can be designed to actually do handwritten code recognition, zip code recognition. So that was 89. And then 98, so please see the timeline here. So same Lee Yakun. It took him another 9 years to come up with a better. Sorry, any question? Okay, so it took him 9 years to come up with a better neural network for a more accurate recognition of the same handwritten digits, digit recognition of handwritten characters. And he called it DNet 5, which if you go to archive, so it is spelled as ARXIV. So X is the Greek alphabet, which is chai. So it actually becomes archive. So archive is open source, or rather public domain collection of scientific articles in the public domain run by Cornell University. And it is one of the go-to places for looking for articles on artificial intelligence, or rather scientific papers on artificial intelligence. So Lee Yakun's paper, if you search Lee Yakun LeeNet 5 on archive, you will find it there. And I would encourage everyone who has a little bent for going deep into things to try and read this paper. It's a beautiful paper, not very difficult to understand. And it lays out the principles by which he designed this 10-layer neural network, which can be called as the first deep neural network, let's say. Because the distinction is basically in the number of layers. It's a simple neural network is 3-layer, and this one is a 10-layer. So you can call this the first deep neural network, which was officially recognized there. So it took him 9 years, and then you can see again the timeline to get an even better accuracy. It took another 14 odd years for Alex, where he proposed the AlexNet, which is the next breakthrough in this particular field. And he solved a little bigger problem, because ImageNet is a large collection of pictures of various types of objects here. And the challenge at that time, and this ImageNet challenge is being run and has been run for a very long time. And it's a public data set which is available, a very large data set. And Alex designed a network where he could recognize a 8-layer network where he could recognize whether it's a cat or a dog or whatever else in the picture, with an accuracy of 84.7%. And now please see the speed at which things start picking up now, because by now the groundwork has been done. It takes time to build things so that the foundation is ready and the building comes up much more quickly. So another 2 years, and you had this visual geometry group, which is a group in Oxford, and we will be covering VGG 16 today. So please take note of this. And VGG 16 was this Oxford group called VGG, which is Visual Geometry Group. They designed this network, which is a 16-layer network, and 19 is, of course, VGG 19 is a 19-layer network. So they designed this network to deliver a 92.7% accuracy. So this I would consider as some sort of a milestone, which is very important, because they published this in the public domain. Which means, and we are going to be using it today. So you'll see the power and effectiveness of that. And from this point onward, any researcher doesn't need to go deep into the entire thing to design his own neural network for convolution neural network. He can simply pick up VGG16 and start using it. So they build a foundation in which someone can build a house very quickly now. So this is a very important step that useful, powerful models start coming out of the public domain. And today there's a whole collection of them out there. So our job has been made, we can stand on the shoulders of giants, and our task has been made much easier now. So I personally think that the next milestone is equally sort of fascinating and amazing in 2016, which is another 2 years later. So there's this team in once again London now, which is DeepMind and which is now a part of Google. So Google bought this for $500 million, and I think it was a great investment they made at that time. And DeepMind team developed this, they call it a GAN, I think, generational adversarial network or whatever. And they designed this AlphaGo to defeat Lee Sedol, who was the reigning world champion of Go at that time. Go is a game which I'm assuming many of you know. But anyway, just to repeat, Go is for Korea and China and some of the countries in that region what cricket is to India. So we think of cricket as religion. And hats off to Avinash Karandikar, because he was my cricket hero at that time in Bhakia. So in any case, so cricket is religion to India, and Go is similar to that for those people, and it is considered a tougher game as compared to chess. So chess, computers defeating like Deep Blue of IBM defeating IBM.
Mr. Gupta. Mr. Gupta,
Yeah.
sorry to interrupt, but is it the same screen that you are showing? Same slide?
Yeah. You're not able to see it?
Okay. No, this is
I'm
only
on the
one
last
slide.
line. Is that Sujoy?
Yes, Sujoy. I am seeing only the first slide, the few application areas. That slide. Are you talking on the same slide?
No. I am on a very different slide. I don't know how you have got to the. Are you looking at? Are you witnessing the thing on a phone or on the PC?
No. On a PC. But I am seeing that slide only. I don't know about the others.
No, but we can see
the slide. There's a problem with the system.
No, sir. We can see the slide DL timelines.
Yeah, real timelines. Yeah. So Sujoy, you'll have to probably reset or something. I don't know what's going on here.
Maybe you can connect again.
Connect what?
I'm saying disconnect and connect again.
Yes.
Yeah, I'll do that. I think.
Try and do that, because I think everybody else is able to see DL timelines there, deep learning timelines there.
Or maybe
Okay, fine.
try a refresh.
Then there's a problem in my system, maybe.
Yeah, please try and see if you can reconnect here.
Yeah, refresh. Just refresh.
Okay. Yeah, correct. Yeah, right.
It'll work. Yeah.
Okay, so AlphaGo. So the Koreans and the Chinese never believed that a computer can defeat Lee Sedol. So it was a moment of epiphany and also of shock for them when the DeepMind team built this AlphaGo, and they had this competition, a publicly demonstrated 3-day competition in which AlphaGo was able to very convincingly defeat Lee Sedol. And I'm told that Xi Jinping, who's the president of China, was so impressed by that event that, in fact, he started reading AI books at that time. And if you see pictures of Xi Jinping in his study, you can actually see the books of AI in his cabinet at the back here. And China today has one of the largest AI programs in the world, very, very aggressive AI domination program of any other country here. So in any case, I think it was a defining moment where they were able to do that. And today they have AlphaGo Plus, which does an even better job here. So it's an amazing feat that which has historical significance. And the other small thing I want to point out, because I know there are some startups in this group also, so you might like to note with great interest the fact that this Forrester Landola, he has a company called DScale. And DeepScale, what they did is something very, very interesting. So he redesigned, or rather restructured the VGG16 program, which we talked about from the Visual Geometry Group of Oxford. And VGG16 has, we'll see that when we do it, when we do our the example today, that VGG16 has about 240 million parameters here. So he developed a network which he calls SqueezeNet, which brought down this entire thing from 240 million parameters to 500,000 parameters. So 1,000 times or 500 times reduction in the size of the parameter set. And this company then got purchased by Tesla. So DeepScale is now a part of Tesla. So you might be wondering why Elon Musk was so fascinated by the work that Landola's company did, and he was willing to spend a lot of money to buy this company. So I'm sure you can guess the answer, but let me try and highlight that. So the latest versions of Tesla Model 3 actually have two computer boards which have a AI specific chip which is custom designed by Tesla. So this is a new wave actually. Custom AI chips which can do very specific jobs here. So you can quite imagine that Tesla is the leader in self-driving today, while autonomous self-driven cars are still, from a regulatory point of view and a safety point of view, are still a little way off. But level 4 driving is still allowed here. Level 4 means that you driver-assisted driving. So the driver can go on autopilot and leave and maybe even take a nap here. But if there's a problem, he is in a position to intervene. So a lot of their work is they have a deep learning AI program which runs on these AI chips in the Tesla Model 3. And as you can quite imagine, that running AI on a cloud with a huge amount of compute power and memory and hardware available with you is one challenge. But running it in a constrained environment on a car on a single board is a very different ballgame here. So they were looking at optimizing so they were not very happy with very large scale models which has 250 million parameters, 240 million parameters. So they wanted something which is much smaller in terms of footprint and can have power consumption, CPU, hardware resources that it requires are much lesser. So that suited Elon Musk a lot. The skill set this company was having, and it got taken over. So the idea is to show you that this is an open field, lot of potential in different dimensions. The work has just got started, and anything you work on will possibly have some relevance in some space. And who knows, if you do something good, you might get acquired by somebody like Elon Musk or some other large company and make $1 million there. So not to set your hopes too high, but there is a lot of potential in my opinion. All right, so little longish coverage of this slide, but I thought it was interesting. It should be interesting for everyone. Any questions on this? Otherwise, we'll move to the next one. Okay, so so this is for my non-technical friends here. So from here onwards, it starts. So we have talked about very general stuff so far, but from here onward, it's going to get a little technical. So please fasten your seatbelt, and just to put you at ease, I have the problem we are going to try and solve now to give you a sense and a taste of what AI can do is this mass detection problem. So I presented a dummy's view of mask detector. If you don't follow much from this point onward, don't worry. If you can stay with just the high level view of what we are going to do, by understanding the problem, clearly the problem that we are going to solve, and just use a black box, treat the AI as a black box there. So like you drive a car. So when you drive a car, you don't have to be a mechanical engineer. You don't have to know the thermodynamics of the IC engine and everything else. You just need to know how to turn the steering, press the brake, the clutch and the gear, and maybe a couple of other things there. So, from a user perspective, this is a definition from a user perspective. Just treat the AI model as a black box. So here is what we are going to do in the mask detector problem. We are going to present the AI model. The model we will develop, we will actually go through how to develop the model, train the model, etc. All that stuff is there. But even if you miss most of it, just treat the model as a black box here. So what are we trying to do? We are trying to feed the model with the picture of a guy with either a mask or without a mask here. And we are asking the model to tell us whether this particular picture, in this particular picture, whether the person was wearing a mask or was not wearing a mask. And what we are asked, the way the model does it is that if it is with a mask, it is, in an ideal sense, it should give a value of 0. But it will give a value between 0 and 1 because it works with a score. It gives you a mathematical score. So if it finds 100% certainty that the picture is with a mask, it will give you a score of 0. If it finds 100% certainty that it's without a mask, it will give you a score of 1. And anywhere in between, it can give you a number saying if it is not completely certain. So all predictions from the model will be in the range of 0 to 1. Our interpretation of the result of the model is that if it is less than 0.5, we will say it's with a mask. If it is without a mask, if it is more than 0.5, then we will interpret the result as saying the AI is telling us that it's without a mask. So this is a very simplified view of the problem we are trying to solve today. Now, one last comment on how we feed the model with the picture. So, although I'm sure everyone understands that, but let me try and put it out in any case for more clarity. The model is all mathematical. So, it doesn't care about the picture really. It cares about the numbers in the picture. So, how do we feed it numbers? So, if you have a JPEG image which your camera or your phone is able to take, then the computer in the digital world is seeing the picture as let's say 100 by 100 grid of pixels. So I'm sure everyone will understand what a pixel is. A pixel is one dot here. Now every dot will have 3 channels because it is in a colored picture you will have RBG. So it has the intensity numbers of R, of B, and for G. So let us say we have a scale of 0 to 255. So take any particular pixel in the image, and it will have say R equal to 100, let's say. So the intensity of red is 100, the intensity of blue is say 150, and the intensity of green is 165. So these 3 numbers represent the pixel as far as the computer is concerned. So you can quite imagine that for a 100 by 100 grid, you will have a set of numbers which is 100 into 100 into 3. So 30,000, let's say. So 30,000 numbers, a set of 30,000 numbers is what you're feeding to the model there. I hope this point is clear, because if you miss this, then I'll be a little disappointed here. I am assuming everybody understands this part here, that you can feed a picture to the model as a set of numbers there.
Yeah, Sudhir, it's okay. Yeah.
Yeah, great. Yeah, I'm so happy to know that we are in sync so far. So, so this is how a picture is fed to the model. The model understands the numbers. It starts processing the numbers, and based on a logic which we'll go discover as we go along, it comes up with a result and saying the score of whether the score is from 0 to 1 for with mask or without mask as a prediction parameter. So this is all the model is doing. So in a very simplified view, this is how it works. And from now onwards, we will try to see what the model. We are going to deep dive in the model now. Once again, just stay with the high level view. And even when we develop the model, just try to understand the process we are following. How do we define the model? How do we compile the model? How do we train the model? How do we test the model? And how do we use it for making our predictions? So if you understand the high level process, I think we'll be fine. So don't get intimidated by the code that is there behind that. While we will cover the code, but even if you don't get the full sense of it, please ignore that and just stay with the high level picture. And the tools that we are going to use, once again, if you get the nomenclature right and you get a sense of what the tools are doing, you should have a reasonable understanding of where we are. Okay, I'm going to move forward now. Okay, so now we are getting into we are opening the hood of the car and trying to see what is inside that thing. So please fasten your seat belts and try to get into. We are going to get a little technical now. But please don't worry, we'll stay with a high level view and a simplified view. Okay, so here are three terms which I want to explain, and this is forming the core of the entire thing actually. What is a neural network? What is a deep neural network? And what is a convolution neural network? Convolution neural network is a type of deep neural network, and so we will just try to get a helicopter view of what these three things mean. Okay, so here is the first little bit technical slide, but since it's a very simplified view, I'm hoping that you will get a sense of it. So we saw in our mask detection problem that to the model we are feeding a set of numbers, and the model is giving you an output from 0 to 1. So here is the inside view of the inside the model. This is a very simple network. So it has three layers: input layer, hidden layer, and output layer. So the input layer is the one which is responsible. So each of these circles that you see here is supposed to represent a neuron. So a neuron is an abstraction. Is just from the human brain, which has 50 billion neurons, that is taken. We are nowhere close to anywhere making networks as big as that.
Sorry, Sudhir, can I interrupt you just for a moment?
Yeah, please.
I hope that you will be sharing all these slides with us so that.
Yeah, I'll send you the slides and also a recording of the entire thing.
Okay, right. Because then we'll be able to focus on what you're saying. Good, great.
Yeah. Please do that. Yeah, please forget about. You can make a few notes if you like, but otherwise, just try to stay focused on. If you stay in sync, I think we'll be fine by the end of the presentation.
Okay, right, great, yeah.
Thank you. So a neuron is a mathematical, is an abstraction. So each of these circles represent a neuron. But in simple terms, a neuron, while it is an abstraction, it's just a name that we have given it. It is actually a very simple mathematical function, let's say. So each neuron represents a small mathematical function. So just an example. So we said that there are a set of numbers that the input layer is fed here. When you feed it to the model. So when you said our JPEG image or the picture we feed it is a set of 30,000 numbers. So let us say that we have, here we have taken only four variables. So variable 1 is fed to one neuron here. So variable 1, let's say, is a number, let's say 50, for example. So you feed a number 50, which is it could be representing anything. It could be representing a pixel. It could be representing a temperature from a temperature sensor. It could be something else here. So the neuron is supposed to do some mathematical function on that. Let's just say the neuron does something very simple, saying multiply by 2. So the input of the neuron is 50. It does a multiplication by 2, and the output of the neuron is 100 here. So it could be as simple as that here. So each neuron is supposed to do a small mathematical function on the input it gets and provide an output here. Okay, I thought this would be fairly simple to understand. So imagine the input layer 1 has four of these neurons. The hidden layer has 3 neurons. each of the input layer neurons is going to feed the output that it generates to each of the hidden layer neurons here. So you can see all the arrows connected to each other. And each of the hidden layer neurons is in turn feeding it to an output neuron, and the output is then getting out there. So what you can see is that the neuron, the neural network has 3 layers. Each layer has a task of taking inputs. The first layer has a task of taking input from the picture. Let's say you fed it. It does some mathematical operation on the inputs that it has received. It provides the result of those operations, the mathematical operations, to the hidden layer. The hidden layer in turn does some mathematical operation and provides the output to the output layer. And the output layer in turn does some consolidation and gives the result here. So you can see that the model is essentially a mathematical paradigm here. It is taking numbers in, it is doing some processing of those numbers and generating and giving some number out there. So if you just get this simple view of our neural network, it's good enough for the moment there. We don't have to go into the, in fact, I have no intention of going into the maths behind all this. Just a conceptual and abstract understanding of what this neural network is doing is good enough for our purpose right now. I hope everyone is okay so far.
Yes.
Okay, thank you so much.
Yeah, okay, good. Yeah.
Thank you, thank you. Okay, now we are going to get a little more tough here in terms of the technicalities there. So we saw a simple neural network with 3 layers. So here is, we are unveiling the great VGG16 here, which to my mind is a great breakthrough because it was put in the public domain. Hundreds of researchers must have spent hundreds of man years of work on creating this network, but they put out the entire network in the public domain so you and me can stand under the shoulders of giants. So it's a great piece of work by the Oxford University team. And here it is unveiled in in all its glory. So let's spend a few minutes in honor of the VGG team and understanding this a little better. So there is an input layer, but there are 16 neural network layers and there is an output layer. Can someone do me the honor of counting the layers and telling me whether they are actually 16 or they are more than that? So actually there are more than 16 here. 14, 15, 16, 17, 18, 19, 20, 21 layers, correct?
Yes.
Okay. So here is the secret behind that why is it called VGG16 when there are actually 21 layers. So the pooling layer is actually not a neural layer. When we come to pooling, we'll understand that. So the yellow ones in each of the sets are actually a block. It is called block 1, block 2, block 3, block 4, block 5, and the final output block. So there are 15 convolution blocks and one final dense layer, dense output block. So the pooling layers, when we see what the pooling layer does, you will realize that it is actually not a neural layer. So we have, when they counted the neural layers, they removed the pooling from the list here. So if you remove the 5 layers of the pooling list, it becomes exactly 16, correct? You guys with me so far?
Yes.
Yes, we are.
Sorry?
Yeah, we are good.
Yeah, great. So there are actually 16 neural layers. Now, so there are 5 blocks and there are 5 convolution blocks and there are 16 neural layers. Now, there are only 2 types of neural layers. One is the convolution layer, which is under con 1, 1. So block 1, layer 1, convolution layer 1, block 1, convolution layer 1, convolution layer block 1, layer 2. Like that, if you see the entire nomenclature, it is very clear. And there are the convolution layers, and there is a pooling layer, and there is a dense layer. So there are 3 types of functions that are there in this particular network: convolution, pooling, and dense. And we'll see a very simplified view of all the 3 so that you get a little comfort of what this damn VGG16 is all about. So I'm going to move one by one and try and give you a sense of what the convolution, pooling, and dense layers actually do. So once again, to keep it simplified, you feed the picture to the VGG16 network as an input. The VGG16 does a series of mathematical operations, gives you a final declaration of what it's found, and gives you a result as the output. So this is exploded view of what the black box when we said AI model as a black box. This is the exploded view of the black box. All right. So convolution 101. So convolution is an extremely simple mathematical operation. So the dark blue is what you want to convolve. Later on, those who are interested can actually read about convolution and understand the full maths behind it. I'm giving an extremely simplified view of the thing. What you want to convolve is the dark blue block. The light blue is what is called a kernel for convolution. And the yellow is the output. So it's a simple mathematical operation. So what you do is you superimpose the light blue on the dark blue matrix here, starting with one corner. So if you start with the top left corner, then the numbers, and if I have to superimpose the kernel is a 3 by 3, whereas the matrix to be convolved is a 5 by 5. So if I were to superimpose, I can only superimpose on 3 of the cells. So I start with the first left-hand corner. So the matrix to be convolved is 1 0 0 0 1 1 1 0 1. Correct? You guys with me so far?
Yes.
Okay. And the kernel is 1 0 0 0 1 1 and 1 0 1. Right?
Mm-hmm.
So there is a simple mathematical operation I need to do between these sets of numbers on the dark blue and the set of numbers in the kernel. And that mathematical operation is a dot matrix multiplication of the matrix. So just not to confuse people who have no interest in the maths part of it, just think of it as a simple multiplication number by number and a summation of the end. So what we are going to do is we'll multiply the corresponding numbers in the dark blue with the light blue. So the corresponding number, the top left left kernel, the number is 1 in the dark blue. It is also 1 in the light blue. So if I multiply the two of them, 1 into 1, I'll get 1, right?
Mm-hmm.
Then you take the next number, which is 0 in dark blue, which is also 0 in light blue. You do 0 into 0, you'll get 0. So like that, if you multiply, there are nine numbers in total which I need to multiply by each other. If you multiply all of them, you will find that you will get only 5 at the end. You'll get 1 plus 1 plus, so 1 plus 0 plus 1 again 0, then 1 plus 1 plus 1 plus 0 plus 1. It's almost, it's actually an exact fit here. They're all matching each other. So all the ones will give you a 1 because it's 1 into 1, and all the zeros will give you a 0 because 0 into 0. So how many ones are there in the light blue?
5.
Yeah, correct. Wonderful. So I just sum them up here. What do I get? I get a 5. So that is the output in the yellow block, which is 5. Correct?
Mm-hmm.
So this is the exact same process I repeat by sliding my kernel along the main matrix to be convolved, and I get an output exactly like this: 5 1 3 2 3 2 and 2 2 4. So I'll leave it to you to sort of try and validate this output matrix later at your own leisure. But I've given you a concept of how convolution works, and not because you need to know it, but just to feel comfortable with the idea that convolution is a very simple mathematical operation. So I hope it's not, people have not found it so frustrating to understand this, and we can move to the next one.
I think you are saying that in a way we have to take this light blue box, fit into the top left corner, or map it and see and multiply the corresponding numbers, then take it below, and then move it towards right.
Exactly.
So there's a possibility of 9 set boxes getting there.
Absolutely. You got it absolutely right there.
Okay, thank you.
If you try this later, you will find that the output matrix is exactly the way we have discussed it.
Gupta ji, can you show some other element of that, how it has come?
एक एग्जांपल और ले लें.
आप एक काम करिए.
Okay, let's do one thing. Sorry, yeah. So we did the top left corner, right?
Yeah, can go to right.
Let us slide it by one on the right, to the right here. So if I slide it to the right, then I will drop the first three numbers on the left column, which is 101, and I will in fact get now 001, 110, 010, which is the center this thing for the blue, dark blue.
Yeah.
Second column, third column, fourth column. First row, second row, third row. 001, 110, 010. Is that right? WhatsApp, ठीक है ना?
Yeah, right.
Yeah, you have moved to the right by one step.
Right. Move to the right.
Gone down. You're not gone down. You're not gone down. You're at the top.
Either way, it doesn't matter.
Okay.
I've just moved it to the right by one.
Yeah.
So if you do exactly the same operation, you will get one as the output. You please try it, but and see if it works for you.
I have not understood.
Not understood or understood?
No, I have not understood.
Okay. So we will do a small dot matrix multiplication of 001, 110, 010, which is on the dark blue, with the light blue matrix, which is exactly the same, 100, 011, 101. Okay?
Okay.
So my first two numbers set of numbers which I need to multiply is 0 on the dark blue, 1 on the light blue.
Okay.
So I get a 0.
Okay.
Then I take the second number, which is column 3, row 1 on the dark blue, which is 0.
Okay.
Light blue, the corresponding number is also 0.
Okay, now I understood.
Yeah. So if you go through like that, all the 9 numbers, you will end up with a 1.
Yes.
Is it okay?
Exactly. Yes, now I understood.
Yeah.
Matching.
One question or one information I need here. So this seems to be a very simplistic model. So all the pictures or all the images that we have, do they go through the same algorithm or similar algorithm?
I couldn't get your question, please. Who's that? Can you identify yourself? I'm not. Since I can't see the picture right now.
I am Sudhir Pant.
हाँ Sudhir, आप बोलिए Sudhir, बताइए.
So I'm asking one question that this seems to be a very simplistic representation. So all the pictures that we have, we will always have this kind of blue picture, and then we can map with a say light blue picture and then convert it into numbers. Is that right?
No, this is just to give a very simplified understanding of what convolution actually means.
Okay. Thank you.
In actual practice, it may be very little different and more intricate than this. Yeah.
Okay. Thank you.
Simply trying to explain convolution as a concept. Yeah.
Okay.
Thank you, Bhatt. Moving to the next one. Max pooling. Yeah. This is even simpler. So I am really hoping that you will find it sort of in a way amusing that it's such a simple one. So max pooling, the idea of max pooling, you would have noticed if you saw VGG 16 architecture clearly, was that after every 2 or 3 convolution layers, there is a max pooling layer. So the idea was that every time you do convolution, the set of numbers explodes because it increases the size of the entire the numbers that are there. So it starts getting you start running into memory problems and all kind of difficulties. So the idea of max pooling is to try to squeeze it actually to back to something which is realistic. So it's trying to reduce the numbers that have got come out of the previous layer. Now, how you do it there? It's a very simple term. So there are 4 blocks in this, in the input that is there in this. There's a light blue block, there's a purple block, there's a red block, and there's a green block.
Mm-hmm.
So it's simply max pooling. You simply pick up the maximum out of any block and put it in the output. So if you see the light blue, there is 5, 1, 2, 3, correct?
Yeah.
So the maximum is 5.
Mm-hmm.
So you simply put 5 there.
Mm.
You choose the maximum out of every block here.
Right. Yeah. Makes
It
sense.
becomes 5, 6, 5, 4. That is the output here. So it's like, you cannot have a simpler thing than this. So max pooling, that is why, since it's not a neural network thing, it is simply a construct to try and simplify or reduce the numbers to a manageable size. That is why we are not counting it as a neural network layer. It's a simple just a function to reduce the number of size of the numbers. Okay, this doesn't need much discussion. It's very simple. So we'll move to the next one. The last item on the list, which is also fairly straightforward, is just a concept again, is a dense layer. So dense layer is a very simple idea. The idea is that you have so H1, H2, H3, H4, H5 is the input, the one which is the dense layer, which takes input from X3, X2, X1. And the simple idea is that every input feeds to every one of the neurons in the dense layer. So you can see X3 connected to all the 5 neurons, which is H1, H2, H3, H4, H5. Exactly the same way X2 is connected to H1, H2, H3, H4, H5. And X1 is connected to H1, H2, H2, H3. So it's every neuron connected to every neuron. That is a simple idea of a dense layer. So it's sort of, the name by itself explains what it implies, but here is a more detailed explanation. So clear, I hope. There are no issues on this, right?
Yes.
Okay, great. So I'll come back to the VG16 and hope that you now have a sense of what each of these layers are doing. So there are all these convolution layers, and every 2 or 3 convolution layers is followed by a pooling layer to reduce the number size. And then the end, there are these 3 dense layers which do some magic, and finally an output is delivered.
Yeah.
So here is the great VGG16 explained in very simple terms. All right, I guess we have made progress, and I'm feeling very satisfied that we have sort of stayed in sync so far.
So yellow layers are pooling layers, is it?
Yeah. Right.
Sorry?
Yellow layers are pooling layers.
Yeah, yellow layers are pooling layers, exactly.
Yeah, because that you are written pooing, that's why I got slightly confused.
Sorry?
You are written it is pooing, that's why I got confused.
Oh, okay. This is a cut-paste job. It should be pooling. Thank you for pointing out, but I also missed it there completely.
Typo.
I disowned the slide here. It's
Okay. No problem. Now I understood.
Thank you for pointing out anyway.
Yeah, I understood. Now it's okay.
Yeah, okay, all right. Okay, so now we can get into something more fun here. So this is really fun here. This slide is my favorite slide. It's a real fun slide here. So you will be a bit surprised to know that a simple task for a human, which could have been the most trivial thing you can think of, for a computer, it took us a long time and a lot of energy and research to get to this point. The simple task was to give a computer a picture of a cat and have it identify that, yes, it is a picture of a cat. So this breakthrough happened by a big team led by my guru, Professor Andrew Ng of Google, Stanford University, who was heading Google AI at that time. It used to be called Team X. And they did this with a lot of effort in 2012. So just 8 years back that the computer understood or rather the neural network understood how to, this BGE16 understood how to, or something equivalent to that, whatever they made at that time. I think they called it Google Net or something. To be able to recognize the image of a cat. So here is the image of a cat fed to BGE16 and how at different, after every block, you remember we had 5 blocks of convolution?
Yeah.
So after every block, if you were to take an output of the computer's numbers and try to picturize them, this is how the cat will look here. So block 1 output, you can see the cat, you can block 2 output, block 3 output. It starts disappearing in terms of the shape of a cat, and the block 5 output is completely abstract. Right? So it's really very, very fascinating to see how the computer is working on the numbers. So intuition, nobody knows exactly what the neural network does. Not even the guy who designed the neural network has a clear idea of what the hell it is doing actually. And that is why there's a bit of magic involved in this entire thing. So what the intuition is that in the first block, it is trying to do edge detection and trying to understand at the high level. It is removing all the unnecessary noise and filtering out everything and trying to see the shape of the face of the cat. In the second block, it is trying to see a little deeper. It's trying to see where the eyes are, where the nose is, and what are the features. So in technical terms, they call it feature extraction here. So it goes deeper and deeper. And by the fifth block, it can probably tell you the size of the eyes is this, the color of the eye is this, the size of the nose is this, the exact location of the nose is this. It has got 2 ears, it's got 1 mouth, it's got whiskers, whatever other features that it thinks are important for it to recognize the cat, it has made exactly a list of that. So it's sort of developed a digital signature of the cat's face.
Great. Yeah.
And then when it does this, you give it another picture of the cat, which is probably a different cat, a different breed of cat or a different color of cat or whatever else. And it matches the digital signature and says, yaar, to cat hi lag raha hai, and then it will declare it a cat. This is how it works here. Okay, good. I thought this was a bit of magic. So I'm happy to share this with you. Next, now we'll go into try and now actually work on the entire problem. We have understood the conceptual level stuff so far. Okay, one more concept level idea before we go, because we'll be using this here. And this is a great idea and very powerful, very fascinating, and really path-breaking. And it's not very old yet. It's just 2 or 3 years old yet. BGE16 was in, I don't remember the date now, but maybe around 2016 only, somewhere around that. So 4 years, 4 or 5. This is only maybe 2 or 3 years at max here. The idea of transfer learning. So please stay with me, and it's a very simple slide, very conceptually very simple, but the idea itself is extremely powerful here. So on the left side, we have a source model. So in our case, the source model is the BGE16 model. The BGE16 model was developed with a very large data set of training data and equally large set of labels. So label is basically, so if there are 1,000 different types of objects, then each label represents one object. So if it's a car, it will say it's a car, that is a label. If it's a bird, it will say it's a bird, so that's a label. So what you do during training is you feed it an image, tell it that it is an image of a car, and the model will try to actually determine whether it's a car or not. If it makes a different prediction, then it will try to back propagate and correct itself. So that is what you do during training. So large set of labels, but okay, large means 1,000 is not all that large either. But ImageNet has a million of images, millions of images, a large set of labels, large model, 500 million parameters to be trained, etc., etc. So it's a huge task here. Only a company, a large group like VGG or Oxford University could do it, or Google can do it, or Facebook can do it. You and me can't do this kind of stuff. We don't have the compute power, we don't have the data, we don't have the resources to do this work. But BGE16 and similar models which are published publicly are available to us. So the idea of transfer learning, how do I take a large public model like BGE16 and retrain it for the specific task that I have in mind? Can I do that? Does it work? And if it has to be done, how do I do it? So what the idea of transfer learning is that you don't start from zero. You start with VGG16 as a pre-trained model which you use here. But I retrain my model on my specific data set and my problem and say, you forget about the rest of the story, please just do this part for me. So can I retrain my model with a much smaller data set and a very specific task to be done and make it do what exactly I'm wanting to do? That is the task of transfer learning. Conceptually, I think it should be clear. By any question, I would be happy to answer. Otherwise, we'll cover this in more detail as we go on.
Seems clear.
Okay. So the beauty is that transfer learning works wonderfly. So the power it has given me is that I can take VGG off the shelf, plug it into my model, retrain it with a few much smaller data set that I am able to get hold of, and make it do a job which is very, very specific for my purpose. So it has given me power which I couldn't have done it earlier. So, and that is what we are going to deploy today. We will take the VGG16. We'll have a small data set of with mask and without mask images, retrain the model on the with mask and without mask images, and see that it actually delivers to me a good result. That is what our objective is going to be today. So what we are learning or trying to do today is only 2 or 3 years old in terms of a conceptual level availability of this kind of an approach, which anyone can do, let's say. So when we say demystify and democratize, this is the idea that you have enormous power in your hand which you can deploy for anything you want to do. Because all this stuff is available publicly at zero cost. Okay, so we have got a hang of transfer learning, and let's move to the next one. Okay, now we are all set there to deep dive into the actual world of AI development, AI model development. We need some tools now. So we are going to focus on the tools here. And believe me, my non-technical friends, please believe me that these tools are number one, free. You don't need even a powerful laptop here. You can use the cloud for doing all this work. So a simple laptop or a simple computer is enough. Nothing to be paid to anyone. It's all free, all available there in the public domain. And it does not require very specialized technical knowledge because a lot of libraries and stuff has been built which you can actually use just by cut paste from here and there. If you have a little understanding of what you're doing, you can get your job done in a fairly straightforward and simple manner. So my intention from here onward, while we are going to deep dive into things which you may feel a little uncomfortable with, but if you try your hand on it, I can guarantee you within 1 day of little effort, you will be able to get fairly comfortable and familiar with this stuff, regardless of whether you have done any programming so far or not. So with that promise, let's move ahead there. So my first weapon in my armory is Google Colab here. So Google Colab, hats off to Google for having made this publicly available. If I have a Google account, which means if I have a Gmail account or any other kind of Google account, it will allow me to use Google Collaboratory cloud services for building, training, deploying, and using an AI model. That is the purpose of Google Collaboratory. It is a free resource on the net, but only if you have a Google account to be able to use for your work for AI. Okay, so we'll just take a quick look at that here. So here's a simplified picture. When we actually come to the practical or the demo, we will open the Google Collaboratory and show you how it works. But just to get you a little familiarity with this, you can see a small arrow, a dark circle with light gray arrow inside that. Can you see that? I can't. Okay. I guess just look at this. When you see it in action, you will understand better. So this is what is, just to give you the terminology clearly. This is using a thing called Jupyter Notebook. So Jupyter Notebook is like an IDE for the guys who have a software background, development environment. So it's a playground for coding. So when you open this, when you go into this and open a notebook, it will give you a blank notebook. This is filled up. So when we actually go to the practical, we will see that it gives you a blank notebook. You can put your code in and run it in that. So it's just a playground for developing your AI code. That's all you need to know for the moment, which you can access free on the net. Okay, now we come to the second tool in our armory, which is Python, because everything is built up on Python. Once again, this is my challenge to my non-technical friends. You spend just 1 hour after this thing and just follow what I'm asking you to do. If you have done no programming, guys who have done programming will anyway find this entire thing very trivial. But if you have never done any programming, trust me, if you follow what I'm saying today, within 1 hour, you will start feeling comfortable. So just to make sure that I don't trivialize it, let me take an example of the Sargam here. So Sare Gama Pa, Padana, Disa, you can, on any instrument, you can learn it within half an hour of effort. But if you want to play a rag, it can take you a lifetime of practice. So don't get carried away by the simplicity of Python. You can spend your lifetime learning Python. You can learn the basics in 1 hour, but you can spend your lifetime in learning Python if you want to be a pro. So with that caveat in mind, while the Python will remind you of a snake, but it's a very powerful programming language, and we are going to go into a bird's eye view of Python in the next couple of slides. Okay. Okay, having been a bit of a techie for most part of my life, I can't help telling you this stuff here. And pardon me for sort of gloating over it, let me say, if nothing else. So there are three, in my mind, very powerful and widely used programming languages in the public domain. One is JavaScript, one is Java, and Python. So JavaScript is for the guys who do web development. Java is for the guys who do enterprise software. But for people who want to do machine learning, Python is the go-to place. And we'll see why. So in the 2020 ranking, Python is actually considered as number 2, and it sort of is JavaScript is of course number 1, but Python and Java both stand as number 2. So it is considered the second most popular programming language in the world today. Okay.
Yeah.
As a novice, because I am not a programmer, while I may be an IT guy, but I am not a programmer. And one thing, because I'm a novice in programming, it is really great for me is that it's an interpreter, which means it is execution line by line. So unlike many other languages where you need to write a full program and then compile it and then try to run it and get an error message and keep debugging and debugging and debugging. Every time here in Python you write a code, you can execute it. Which I really love this feature in Python. So with these small inputs, let me actually now get into deep dive into the thing. So here is what I call my first Python program. So it's a little smallish on the screen. We'll actually do this when we get to it. So what do you need to do? You need to open a notebook in Collaboratory. You need to write 4 lines of code here. And you can declare yourself to be a Python programmer. Even if you have done no programming in the past, you declare one variable A and give it a value of 3. In the second line, you declare a variable B, you give it a value of 4. You declare a third variable C and you say it is equal to A plus B, and then you do a print C. Can everyone see this part, the 4 lines here?
Mm-hmm.
So it gives you 7.
Yeah, sure.
So it's the simplest program in Python you can write. And the moment you've done this program, you can say that you're a Python programmer. Know this thing. I can't imagine how it can get simpler than this. So, it's Python programming is built into the Collaboratory. So you don't have to do anything else. Setting up the environment, no nothing. Just start doing Python programming straight off the bat.
Right.
So everyone on the thread can actually promises me that after we are done with this workshop, he will open a Google Collaboratory and try these 4 lines of code and declare himself a Python programmer. Do I have a promise?
Yes, sir. You do have. A
Hey, I am going to really quiz you on this later. Okay. While we have become a Python programmer now, here is just 2 or 3 inputs which I think are very important and interesting to keep in mind when you start doing even a basic level of Python programming. So in any language, you have data types there.
Sudhir, just one moment.
Yeah, please.
Google Colab, you can use Python, but don't you have to load Anaconda and then all this?
Nothing, boss. I'll show you actually. I'll show you when we end.
Okay, right. Okay.
Nothing is required. It's already there. Everything is built into it. We'll come to it and see it. Okay. So all languages have a data type here. So Python has 4 data types here, which are very elementary, and I'm sure you can sort of imagine them. But I have put them down here so that you're very clear of how to declare it and how to check. This can be intricate when you are actually doing programming and you find that you have reached something and the data type is not matching, will give you an error message. So the ability to check a data type is interesting and important here. So integer. So basic maths, school level maths, you know what an integer is. If I don't have a decimal, it's an integer. So if I say x is equal to 5, and this is you're finding out data type in Python, you simply say type and you put in bracket the variable. So if you ask for type x, what is the type of x, it'll straight away tell you it's an integer. I have not declared as an integer, it has understood it's an integer. Floating point is the next one. So if instead of typing 5, x is equal to 5, I say x is equal to 5.0, and then you type, you ask for what is the data type, it will tell you floating point here. So everyone knows what is floating point because decimals are stored as floating point in computers.
Mm-hmm.
So here is floating point. The third is a string. As you can quite imagine, names, age, all kinds of other things I would like to store as a string, which means a set of alphabetical characters. So if I put x is equal to, and I put a apostrophe and say let's say type hello, or you could type anything for that matter, any set of characters, and you close it with an apostrophe, the Python will understand that you're feeding in a string type. It's called a string type. So if you ask for type, what is the data type, it will tell you str, which is string. And the last is a Boolean. So Boolean, as you can imagine, is true or false here. So if you want to tell that, let's say if I ask a question in Python for a particular image and ask, is it width mask? Or you try to tell it it's with mask. You can define a Boolean variable and say it's true or it is false. So if you type with a capital T as true or capital F and false, x is equal to true or x is equal to false, Python will understand you are defining a Boolean variable. And if you ask for type, it will tell you BOL, which is Boolean. Okay, fairly simple. I don't think it needs any discussion really. For any question, I'll be happy to answer. Okay. The last thing, and please note this one, because at least one of these data structures we'll be using in our program. So when you see that, if you have understood this, you'll relate to that. So data structure is basically an abstract or a construct of how to store data. So we know data type, but how do I store a set of data? So if I want to store a set of integers or a set of any kind of data, then there are different data structures in which I can store them. The simplest and the most simple, the first one is what is called a tuple in Python. So if I say x is equal to, and you put a bracket and say 1, 2, 3, it will store this as a set. So if I want to, in the third, if I say type X, it gives me tuple. Python will tell me you have stored a tuple here. The data structure is a tuple. And then you do a print X, it will print out the entire set here. So unlike storing X is equal to 5, here you were able to store a set of numbers. So this is the first simple data structure. The second is a list. So in the list, basically, and the list could be numbers, it could be string, it could be Boolean, it could be anything. So you create a list and you have the square bracket for that. And you say 1, 2, 3. If you start and end with a square bracket, it will understand that you're storing a list. And you ask for type and it will give you list. And then you print X, it will give you the entire set as a list. The last is a dictionary. So dictionary, basically you have a name value pair. So A is 1, B is 2, and C is 3. So it could be name, age, gender, for example. So you could say name as a string, so you can see the apostrophe there, and you put a colon, and then you say name, whatever, as a string again, say Sudhir. Then age, whatever number there, and gender, whatever. So then it stores it as a dictionary. And now you ask it for a type, it will give you dictionary. And if you do a print, it will print the entire set. So unlike a tuple where you cannot change the data once you have defined it as a tuple, in a list and in a dictionary, you have access to every pair or every element in the list, and you can actually retrieve it. You can do a read and you can do a write. In tuple, you can only do a read, you can't do a write. So we'll be using the list in our program. So I just want you to note the square brackets. Only takeaway from the slide as far as immediate requirement is concerned is that you just note the square brackets and the fact that you can define a list by enclosing whatever you want to put in the list as a square bracket. Fairly simple. I hope it makes sense. With these three things, data type, data structure, and the basic programming methodology in Python, we are good to understand the rest of the code that is coming through. I've just picked up those parts which are okay for you to get a sense of the rest of the story. Okay. I hope it was not okay. I'm sorry I missed one item, which is the flow control layer, which we'll also be using here. So my BARC friends will remember the Fortran days. We used to run to BESM6 to program all this stuff. And the for loop was a sort of a forte for everything. And here is a for loop in Python there. As simple as it can get. For I in range in bracket 10 and a colon. It's just, here I'm saying print I, but you could actually put in any set there, any list of commands there. So if you say print I, it is printing it 10 times. If I had put, instead of in the range brackets, if I had put 15, it would have printed 15 times. So 0 to 14. So this is a simple for loop implementation. So I've just showed it to you here so that when you come to the code, you'll understand that. Okay. So it's a simple iteration that you do repeatedly, some task by take it to a set of iterations. All right. So the third weapon in our armory, which is the TensorFlow. Now it gets really interesting here. So TensorFlow is built on top of Python. So as an underlying layer, you still have Python. But this is a TensorFlow is a Google tool here. So there are many other tools like this here, and many other frameworks. But I have stuck to Google for whatever reason, and we are going to use TensorFlow. So I've just wanted to give you a sense of what TensorFlow does. So TensorFlow is a specific AI programming environment. So it has all the methodologies that you would possibly need in an AI situation, and it's a little different from Python, but it rides on top of Python. And I'll just show you a simple program, let's say in TensorFlow, to give you a sense of comfort. Although we are not going to use TensorFlow as TensorFlow at all. We are going to go one layer above that. But since we'll be talking about TensorFlow a lot of times and we have to load the libraries, etc., I just wanted to understand that there is something called TensorFlow, and TensorFlow version 2.0, which came recently, which solved a big problem as far as I'm concerned, because as I told you as a novice programmer, I like to see my program execution step by step. So TensorFlow 1.0 never allowed me to do that. I had to write the whole program first and then execute it, and I would struggle for hours to try to debug it. TensorFlow, after a lot of user feedback, they realized that there are many novices like me out there who need step by step. So TensorFlow has allowed step by step execution, which makes it really great for even beginners to try and understand this in a very simple way. So here is the great TensorFlow. So as you can see, it's version 2.x now. And a simple command like import TensorFlow as TF is what we use to get load the libraries. And a simple, very simple, like our ABC program, I've done the simple ABC program here. So the only difference is that the syntax is different here. So since the tensor is in Google TensorFlow is defined slightly differently. So you have to, even if you want to give it a constant value, you have to say A is equal to TF, that which means TensorFlow dot constant, and then say, so data type is being explicitly defined here. It doesn't, like unlike Python, which determines the data type on its own, here you would tell it that. And B is equal to 4, then you say TF dot multiply. So there's an explicit command here. There you could simply use a star and do the multiplication. Here you need to type it out as multiply and then in bracket A and B and say specifically all that stuff and then print C. So it gives you TensorFlow, the value of A into B is 8. It gives you a shape, it gives you data type. So it's a little more explicit in many ways, which whatever reason this is how they've done it here. But since we don't end up using TensorFlow directly, we use Keras. So it doesn't bother us too much, but just to get you familiar with the terminology. Okay, here's a great Keras. So Keras is a godsend for guys like me and you, where we don't want to do any hard programming work. We would like to use things which already people have done, right on sit on the shoulders of giants. We don't want to reinvent the wheel and so on and so forth. So Keras does all the hard work. So it's a great tool for building models, for compiling models, for training models, and using models for prediction. So it is a huge library. It's got a huge variety of stuff. We are going to use something very specific out of that. And so I'll focus only on the part which makes sense, which is interesting for us right now. So Keras is also a Google tool now. It was done by a Google team, but it was a little separate from TensorFlow. Now it's totally integrated with TensorFlow. So Python, TensorFlow, and Keras forms a complete set now. And the collaboratory, all tightly integrated. So it becomes very easy for anyone to actually use this entire set and do his work here. So here is what the steps in. This is important and interesting. So please pay attention to this one. Don't go into the micros of the thing right now. Just understand the high level idea. So one set of commands to define the model. So model is equal to keras.sequential and a set of variables, instructions after that, which I'm going to ignore for the moment. But there is a model building part which is extremely simple in Keras. Then one single command for compile, model.compile. One single command for training the model, model.fit. One simple command for evaluating the model on a test data set, model.evaluate. One simple command for model.predict, for predictions. So just these 5 steps which are there. Building the model, compiling the model, training the model, evaluating the model, and predictions based on the model. And it gives you a very simplified set of commands to use them. So there is a whole lot of science behind the intricacies of each of these. But if you want to start using them in a simplified fashion, it's not a great deal. So if you just understand this basic methodology, then you can start building and training and using models. I can't imagine what can be simpler than this. Okay, sir. The tools are all there. You have all the weapons in your armory, and we can actually deep dive into the code now. Any questions so far? I hope I have people with me, or I've lost everyone there.
I'm still around.
Yeah, we are with you.
Okay.
Yes,
Abhay,
we are.
can you validate that we are okay?
Yes.
Yeah, we are with you, but my internet is giving me trouble. So in between, I lost you a little bit.
So we'll touch base later. But anyway, still try to stay with us on the rest of the story.
Yeah, I'll stay with you.
Okay, great. All right, I'm hoping that I'm not scared everyone away. And let's move to, I'll be courageous and try to move to the next one, because now we are going to apply actually all of this stuff in the real world. Okay, so coming back to our mask detector problem. So just to recapitulate, we said that we will feed a JPEG image to the model. The model will tell us, give a score of 0 to 1. 0 means, closer to 0 means that there is a mask the person is wearing. Closer to 1, that he is not wearing a mask. So we are now going to look at under the hood, what is the code and what does it do? We have covered a lot of ground. If you have followed so far what we have done so far, you will be able to get a sense. Don't go into the nitty-gritties of it, but you will get a sense of the flow of the entire thing, of what the code is doing. And if you just copy paste and use it, it will work for you. So you'll get a sense of actually how it actually works in practice. So don't worry about the finer details of everything right now. Just stay with the high-level view. Okay, to define the problem more clearly, just to give due credit, I used the data set of a good lady. She's a machine learning engineer in Bangalore with some company. She created this data set. Pranja Bhandari is her name. And she created the data set. So I'm riding on top of her data. There are 690 images with mask and 686 without mask. So the flow will be that we load the images from her data set into our system. We will load them from our system into the model, pre-process the images for a few things that the model needs to see them in a particular format. We will define a model, then we will train the model on these images, and then we will test them on the test set. And then we will finally do some predictions based on some of the images that are there in this, and try to get, or with a completely new image if required, and try to see if the model is doing something useful or not. Okay, ready to go to the next one?
Yes.
Okay, great. So when we do come to the practice session, here is my collaboratory from which the code can be loaded. So I'm not expecting you to rewrite the code at all. My GitHub is under the name of Sudhir 2016. This is when I started doing all this stuff. And you can see in this image that Google Colab 10 BGG16 based mask detector. Can you see that?
Yes.
The first one. Yeah, first one. So if you go to this, my collaboratory, my GitHub account, and you click on this, it will give you my code, and you can simply when I actually run it, I'll show it to you. You simply click on open with collaboratory, and the code opens up in the collaboratory directly, and then you can straight away run it there. So I mean, it cannot be simpler than that. Yeah, you can simply get hold of the code and start running it within a couple of clicks. Yeah, actually. All right. So before we actually run the code, I needed to show you in 3 slides the very basic building blocks and a high-level view of how it works here. So this is the first block of code. So you can see there is this light blue open in Colab. Can you see that?
Yes.
Yeah. So when you do see the code in GitHub, if you click on open in Collab, it will straight away bring the code into Collab for you. But you must have your Google account already logged in there. Otherwise, it will ask you to log in. So you can see the code in Collab. And now I'm going to run through the code. We'll do a walkthrough through the code to get a sense of what it's doing, and before we actually try and run it there. So the first two, this is the first page. The first two blocks, there's a lot of import functions there. So from TensorFlow, import TensorFlow STF, which we talked about. So there is something called numerical Python. So import NP, numerical Python or NumPy as NP. Import the matholib.py plot, Python plot as plot, etc., etc., etc. So don't worry about all this stuff. Right? And there's a lot of Keras stuff that is reported here. So don't worry about all this. This is simply to tell sensitize the notebook that you're going to need all these things. So it should keep them ready. So you simply click on the execute button in each of these two blocks, and it will get hold of all these libraries for you. Okay. So the real action starts in the line below that, which is, if you can see, there is a colon there, and then git clone. Can you see the git clone command? And there is a URL after that, https ://github.com, etc., etc., etc. Can you see that? Yeah. So git clone is a simple command. If you do git clone, so GitHub is from git clone. So git clone command basically, and you give it the URL of the library you want to the stuff that you want to get. Then it will actually clone the entire thing or get all the data into your system there. So it's a very simple command to get hold of all the data that Prajna has put in the data set which Prajna has put in her GitHub. Okay. Now we come to the list function here, which I talked about when we discussed the data types here. So you remember the list data type?
Mm-hmm.
Okay. So we are going to define two empty lists here. So you can see there are two square brackets, X and Y. And there is nothing in that. So it's a null list. There's nothing, it's an empty list. But we are going to define the list ready so that we can then start putting the data in that. So these are the three simple things. We load the libraries, we get hold of data from Prajna's GitHub, and we define two, X and X is the input and Y is the label. So you remember the input data and the label, correct? You said, we said that if it's a cat, then it should be labeled as cat, and if it's a dog, it should be labeled as dog. And in our case, it's with mask, so you should label it with mask, and if it's without mask, we should label as without mask. So Y is the label and X is the data. So X in our case is the image of the face with or without mask, and Y is the label. So I want to get the X and Y. So as you can imagine, during training, I'll need to feed the training data, which is the images and the labels, to the network, so it can to the model, so that it can actually train itself. Correct? Right. So X and Y are empty lists which I have defined. So these are three simple things that I'm doing in this part of the code. Okay, I'll move to the next one now. So the first command, don't go into the interfaces, just understand that there is a imread file command, which is basically for reading files there. So it is reading, and you give it, there is a URL there, glob.glob, and then contained observations, experiments, data with mask. So just forget about everything else. Just remember that this command is for loading the with mask images. Okay. Yes. And then the length and image command is to tell me how many images I have loaded here. So I remember that I said that there are 690 or odd images for with mask and 686 odd images without mask here.
Mm-hmm.
If the length command gives me the correct number, I know that I have loaded all my images.
Okay.
Now, once I've loaded, this command is for loading the images. Now there is a for loop. We discussed the for loop. So you can see the range is exactly 690. So we set 690 images which are there for the with mask here. So essentially what I'm doing is for I in range 690, I'm iterating on each of the images, correct?
Yes.
So for each image, I do 4 things. So the CV2 command is basically to get hold of the image and resize it, because I need to do give the image to the computer or the model in a certain size, and the size is 244 by 244. So it says size 244 by 244. So resize, so it is resizing the image, and then there is an append command where this image is put into the data set, into the list. So the X list, remember, is the one with for the images, and it was a null list with a blank list in the beginning. So for every image in the for loop, one by one, I'm going to put inside the list, which is X. Correct?
Yes.
Okay, and since these sets of images are without mask, or rather with mask, and I said that with mask means 0 in the ideal case, so the label is 0, and so out is 0, and y dot append out, which means basically in the y list I'll put a 0 there. So essentially, after this for loop is executed, I should have 690 with mask images, and the y list should contain all zeros for 690 zeros, saying that all these numbers are without mask. All these images are without mask, or with mask, I'm sorry.
So all these 690 images have been labeled 0.
Yeah, exactly.
Okay.
Okay. I do exactly the same thing by the next 3 commands for the without mask. I'm not going to repeat the discussion, because you can see it's a carbon copy or a mirror image of the first 3 sets. So there was 686 images which are without mask. So it is doing it. The iteration is for 0 to 686.
Okay.
So by the end of these commands, I should have my X data set should have 690 plus 686 images.
Right.
Both with and without mask, and my label data set should have 690 plus 686, 0 and 1 numbers there.
Right.
Which represent the 0 and 1. Okay?
Yes.
I hope I have not lost everyone here. Ask me anything you want, because this is the crux of the entire thing. In any case, everything else is simple after this.
No, it's okay. We are trying to get a hang of it.
Yeah, good job done, Sudhir.
थैंक यू यार. तो ये तो बिल्कुल सिंप्लीफाइड वर्जन से इसको हमने इमेज को एक एक करके लोड कर लिया, उसको लेबल कर दिया और डेटा सेट सेव कर लिया.
It's very interesting. Yeah.
Okay, so we'll move forward again now, and I'll ignore these NP array, and NP array is just a slight pre-processing of the data. I'll ignore this for the moment. The next crucial command is the train, splitting the data set into training and testing. So you will notice a command there: train X, train Y, train X, train test X, and train Y, train test Y. And there's a split defined as 0.2, which means that the test set, 80% of the images I'm going to use for training the model and 20% for testing it. So when I do an evaluation, so why we need to do this is an important point actually. I always split my data set into 2 parts. And the training is obviously the bigger data set, testing is the smaller one. So I train the image on the training set, and then so the model has never seen the test images before. So when I test it, it is supposed to give me a number and accuracy and say how well it performed on the test data set, which was not the training data set. Very important feedback how the model is doing it.
Right. Yeah.
So this command is simply for splitting the data set into 2 parts. 80% test, 80% train, and 20% test. Okay, yeah. So I think we are 90% there, and the last few sets are fairly straightforward. So the next thing is I am now going to build the model. I have my data ready now. I have split the data into test and train, or rather train and test. And now I am now going to define the model. So you remember that the base model is supposed to be BGG16. So the first command is base model is equal to BGG16, and there are a set of things after that which you can ignore for the moment. But one thing you can notice that include top is equal to false. So this is simple command with all the work that the good guys in Oxford have done is now brought into my system by just a single command. But I have told the system I don't want the top because I want to train the top myself. The top is the last layer, last set of layers.
Okay.
So I will use the 5 convolution blocks, etc. But the last few layers I will train myself to suit my particular purpose, which is on my data set. You remember transfer learning? We said we'll use the basic structure of the original model, but we will slightly retrain it for our purpose.
Yeah.
You remember that, right?
Yes.
Okay. So if I do include top is equal to false, it will ignore the last couple of layers of the basic BGG model and allow me to train them, train it as per my need. Next command, I simply define that I need to make the last few layers, the base layer is the okay, but I need to be, so it is basically saying, don't train the core model, which is the base model, only for me, train for me the final layers, which I'm going to define now. So it says layers are equal to trainable is equal to false, which means don't touch, when you do training, don't touch the core model. Just train the last few layers which I'm going to define.
Okay.
Okay, then now the head model, which is, since I said I don't want to include the top, I have to define my own top here. So don't worry about the rest of it. There is something called like you had. So it says base model is equal to base model, output of base model. So this is going to, the head model is going to take the base model output and do a couple of things on its own after that. And you can see a couple of layers there like average pooling. So average pooling is something similar to max pooling, except that you take an average instead of taking the maximum.
Okay. Yeah.
There's a dense layer, there's a dropout layer, which is, I'm not going to go to the intricacies of that. There's another dense layer. There's a couple of layers I want to put in here for training them on my own, for my need. And the final model is equal to model, which is input model, base model, plus the output of the base head model. So this is the sort of, you could say plastic surgery I have done. I have, like Ganeshji, I have removed the head and put a different head. I have put a different head here. And I have now a composite model, which is a combination of BG16 plus my own couple of layers. Okay?
Yeah.
Then you just compile it. There is a summary command for giving me what my model is, just to tell me what my summary of my model is. Then you train it, and then you evaluate it, and then you make prediction. There you're good to go. So all the hard work done here.
Yeah. Train the model, evaluate the model.
I am really hoping we are in sync here.
Can you go through some of the code lines for since moving forward from training the model? Like explain what you put in this.
Train the model, okay? Train the model. Okay. Model fit, model.fit. The command as we saw earlier for training the model is model.fit. So I'm simply saying train it on train X, train Y, because you remember that we defined data set as we split the data set of X and Y into 2 parts, the training and the testing.
Yes.
So we said we are saying that please get the data from train X and train Y. Then there is something called an epoch 5. So we are saying here you should actually run, when we run it, I'll show it to you that we should actually run it for 10 times. But I'm doing it 5 because it takes too long otherwise. So to save on time, I put it 5 here, right? So it won't give me an as accurate a result as I should be getting, but it's still good enough here. So just for our own purpose, it's okay. So epoch 5 means you train it 5 times here. So what it does is trains it at one pass, it goes through the entire data and it sets the parameters. Then it does that again and it does it again and it does it again 5 times. Every time when we actually run it, you will see that the loss starts improving and the accuracy starts going up. So if you do it 10 times, it becomes even better. So it needs several rounds of training before it can become a good model. So your epoch means how many times you want to train it.
Okay.
And the shuffle basically says that shuffle my data so that it doesn't see the same pattern again and again and tries to construe that every 10th. So I don't want the model to be over smart and start understanding that my first 690 were with mask and after that they were without mask. So if it develops a very simplistic understanding, the moment I deviate from that pattern, it will go crazy. So shuffle means that I wanted to really look at the picture carefully and not try to fool me. So that is why shuffle is equal to true is important for us. Okay, anything else you would like me to tell you?
The verify prediction command, I don't understand that completely.
Okay. So let's look at the model.evaluate first here. So like we did the training on X and Y, train X, train Y. You remember that the testing, we split the data set into train and test. So we labeled the training set as train X, train Y. We labeled the testing one as test X and test Y, correct? So when I do evaluation, I need to tell it where to get the evaluation data from. So I'm simply saying evaluate on test X and test Y.
Okay.
Okay. Now when you say predict, I need to say feed a value. So predict on what there? So X is the image on is the identification of the image on which you want to train it. Okay. If I say X, if I give a value say 50 here, so it will take the 50th image and try to tell me whether it is with mask or without mask.
Okay.
So it's just X is the input into the. I'm so sorry. I have confused you and I've given you a wrong feedback here. Here it says that you do a prediction. You set up a matrix of prediction scores for the entire X variable set here. So all these 600, 690 plus 686 images, you try and see your prediction score for all of them. Then in the next command, when I say P and I say, so P is the matrix which has the entire prediction score for all the images.
Okay.
And then when I say P 1000 in the next line, it gives me, if you see there, it gives me a number. So in the number in the answer, the red is the answer. So P is what I asked it to do. So I asked it, what is the score for image number 1000?
Okay. Yeah. Okay. Now
and then it says the score was 0.85. So if you remember, we said after 690, all the images are without mask. And every image, if it is without mask, we want to give it a score as close to 1 as possible. More than 0.5 is without mask, less than 0.5 is with mask.
Right. That's clear now. Yes.
So the model, if it has done a good job, is expected to give me any number I feed. If I say P5 or P50, it is a with mask image and it should give me an answer which is less than 0.5.
Okay. Right.
Okay?
Yes.
All right. So we are done and through here. I am so exhilarated that it seems that I have not lost you guys. So Abhay, please validate there.
We are hanging in there thanks to your patience.
अरे यार मेरे तो अबे
अविनाश
नहीं अविनाश को तो समझ में आ ही गया हो यार तो अब मैं अबे हमारे मेरा जो फीडबैक देने वाले थे ना जो नॉन टेक्निकल पॉइंट
हाँ उनको पूछ लीजिए
अबे है नहीं शायद सुजय I think I've lost all the guys who were home supposed to be. I have not seen who's there, who's not there right now. So anyway, hopefully that whoever is there has got some sense of it. Yeah. Okay, so any questions so far? Otherwise, we can actually execute the code.
I would love to see that. Oh, what is the question? Okay.
All right. So let's see the actual. We'll run the car now. We have seen how the car works, and the idea is to actually run it. So you can still hear me, I'm assuming, right?
Yeah.
Okay. So as I promised you, I will go to my collab now, my GitHub, and get hold of the code there. So I am going to ask for. I'm going to go do a Google search of GitHub. B2016. This is my GitHub repository. So you can show it shows me Sudhir 2016. I simply click on that, and here is the page I showed you in the presentation. Okay.
Yeah.
So you can see there are 12. If I click on repositories, it shows me there are 12 repositories, and the one that I'm interested in right now is the Google Colab 10, which we discussed. Correct. So I simply click on Google Colab 10, and it gives me two files. So one is the README file, which you can see what is there in the README file. It's a simple explanation of what is there in this in the code here. We've already gone through all that, so I'm not going to talk about it. So the one code file is ends with .pynb Python basically. So I simply click on this, and here is the code that we have been talking about all morning.
Yeah.
It's all there, and is all the gory details of the code are here in this. And it's the same stuff that we just talked about. It's just what it is in the GitHub right now. So I've opened the code in GitHub right now. Okay. So what do I need to do? I need to say open in collaboratory. Can you see this here? Open in collab.
Yes.
So I simply click that, and there, like a good guy, Google is now sort of opening it in the collaboratory. Okay.
Yeah.
So before I start executing this code, I want to just show. I promise that I'll show you how to open a fresh collab and try to write the first Python program. So all my friends who are non-technical have promised me they will try to write a simple Python program, and this is how you do it. So go to File. You can see File here on the top left. So new notebook. Okay. So here's how a completely new notebook looks. Okay, so I said we need to type 4. So who is going to tell me what are the 4 lines of code I need to type for my first Python program? I wish you could have done it yourself, but let me do it on your behalf here. So tell me what is the first line. So I've typed a code here.
X is equal to a number.
Okay, I said A actually, so let's just use the same thing. A is equal to 5, let's say. Okay, I said this is the button I need to press to execute it.
Okay.
So it's going to take some time because it has to connect to the net, to the cloud to get hold of some things and then start working. So it will be a little slow in the beginning, but once the connection is established, it will be fast. Okay. So it stopped running, so it's now fine. It's done. It is set A is equal to 5 for me. Now this command you can see here. So a plus command. So it basically says enter the second line now. So I said B is equal to. So give me a number. Say 7.
Yeah.
Okay. So here is B is equal to 7. Okay. I now put my third line. So C is equal to what?
A plus B.
A plus B. Correct. Wonderful. There you go. Okay. My last command is now print C.
Print C, yeah.
So does it give a correct answer? Can you clap for Python?
Yes.
All right, sir. So my non-technical friends, if please do me the honor of opening. I've showed you exactly how to do it. Please do me the honor of writing these 4 lines of code and trying it out for yourself, and then you can declare yourself a Python programmer. And I feel happy after that. Okay, so I'm going to jokes apart, I'm going to close this collaboratory now because it's done its job, and I'll come back to my main code. Okay, so this small icon here is basically what the collaboratory, what are the files the collaboratory has.
Okay.
It will take some time to connect to the environment. Okay, before I go, I want to just show you something interesting. Under edit, there is a small command known as notebook settings. Okay. Can you see hardware accelerator here? So what does it say here?
GPU. Why GPU? Yeah.
GPU. So can someone tell me what is the GPU? It's a graphical processing unit. It's about 10 times faster than a normal CPU.
Oh, really? Okay.
So Google, hats off to them here. It's given me free access to the GPU here. And since my code is a little heavy, it needs a GPU. I have set it to a GPU. I could have done none, and it could have given me a normal thing, which would have taken me a longer time to execute. But I actually set it to a GPU. There is something called a TPU also in this, which is a tensor processing unit. I've never tried using it. I don't think I'll never need it. GPU is good enough for me. But it also gives you an option of TPU just for your information. Okay, so the directory says sample data. So this is all stuff that Google has already put into it. I'm not interested in their sample data. I want to put my own data. So I'm going to start executing my code so I can get the data from the GitHub of Prajna. So I execute the first line. It is warning me that this is not authored by Google. I know it is not authored by Google, but run anyway. So it simply tells me that using TensorFlow as a background, as a backend. And I run the second block, which gets in some Jira stuff. So as I promised you, you don't have to go to the details of all these things. You just simply load these libraries, and then you are okay. Now I come to the main command, which is the get clone command. So this single line of code is going to get Prajna's data set for me, and I can see the data set here. So I'm going to show you that part. So it has brought in the data set from Prajna's thing, but it is not. It probably takes a little time to show up in
sample data.
No, it won't be in the sample. It should be outside that.
Oh, really?
Yeah. So this is the file it is brought in. Okay. So you can see that what we need, what we are looking for, is lying hidden somewhere, which is this stuff called with mask and without mask. So there are all these 690 images with mask.
Okay.
Similarly, there are all. I'm going to close this, and without mask, you can see there are all these 686 images. Okay.
Right.
So I have showed you that we can get hold of it by a very simple means and then verify that all my images have come. Now I'm going to do the next step of defining my 2x by the image and label data set as a blank list. Okay.
Okay.
All right. Now I am going to get hold of my images. So it is now loading it into the system from the directory. So it has brought in all the images from the with mask images. and I want to verify whether it's 690. So it says 690 images. Okay.
Yes. Length of image.
Now I want to add all these 690 images to my X data set or X test. It is done that way. Okay.
Yes.
Now I want to do exactly the same thing for without mask. So it says I've got 686 images.
Yeah. 686.
Now I'll load them exactly the same way for the without mask images. So I said there are two small processing steps which I need to do for converting it to an array, which I'm not going to discuss now, X and Y. Now I'm all set to split my data set into 80% train and 20% test. Okay?
Yeah.
Now I'm defining my base model, which is my VGG16 model. So it is getting those 500 billion parameters, half a billion parameters. We brought all those parameters here, and you can see the numbers here. Exact number of parameters that is.
I rated 9 to 8.
Okay, I said I want to declare all my layers in the base model as untrainable. Now I said I'll define my base model, head model. So there are all these layers which I need to define.
Right.
I do my final model as a base model plus the head model which I define. Now I compile the base model, compile the full model. And here is my model summary. For you, if you have the patience, you can see there are 14 million total parameters which are there in this, which are trainable parameters. It's not talking about the parameters that is brought from the VGG16. My own head layers have 14 million parameters for training. And here are all these input layers. You remember block 1, 2 convolution, 1 pooling, 2 convolution, 1 pooling, 3 convolution, 1 pooling, etc., etc., etc. It goes on to the VGG16. And then my average pooling comes in here, the flattened, dense, and 2 dense layers that I've done one dropout. So it is that Ganeshji model now with the head from my own head and the rest of the body from VGG16 here. Okay. Now we do the real final and the fun stuff, which is train this model, and you see what happens during training. So it does epoch 1, which is the first set of training, in 5 parts. It does it in batches. So it split the training data set into 5 parts, and it does the first part, and it says the loss. Can you see here? 11 seconds it took. 307 milliseconds per step. The loss is 0.6. So the higher the loss, the is bad for the model. So the loss should be low and the accuracy should be high. So loss is 0.6, the accuracy is 69%. So you need to read it as 69%. Can you see this here? 69%?
Yeah.
0.69, which is 69% here. So in the second epoch, the accuracy improved, the loss reduced and the accuracy improved to 87%. In the third epoch, it went up to 91%. The fourth epoch, it went up to 93%. And the fifth epoch, it went up to 95%. If I had done all 10 epochs, it would have given me 98% or 97 point some number. It would have improved further. But as you can see, it's a little, it takes a little time. Not all, because I use the GPU, it's very fast. It would have taken me half an hour. Okay. So we'll stay with only this accuracy right now. And let's see what it does, what accuracy it gives me now on the evaluate when it does the run on the test data set. This is my real test here. Because training, it can keep improving because it knows what is there. You already given the label, but here it doesn't know.
Nice.
So it has given me a 97% accuracy even here. I don't know how it managed this. Okay, so I built a prediction matrix now. As you can see, it is predicting for more than 1,000 images. So it's going to take a little time. Okay. So this is the same image that I said. So it's given me, I don't know, the accuracy seems to improve. So it's given me a 0.92 number. So it says it's the score is 0.92, which essentially means that it is saying it's a without mask image. Okay. The last line is just to show you that image so that you can verify yourself. As you can see, the image is without a mask.
Okay.
So I'll just take another example of just say P10 as an image with without a mask, with a mask, and you can see it's given me 0.2229 or whatever, which means it is saying it is with a mask. Okay? And we'll show that image to see whether it, no, it's sorry. I didn't change the number. Okay, there you are. There you are.
That deserves a round of applause for that. Great.
So I want the feedback, boss. How many people have I lost and how many are still with me?
Fantastic. I'm there, sir.
Eh?
I'm there.
I'm here, sir.
Fantastic, Sudhir.
Thank you so much. Yeah. So I am assuming that generally people have got some value out of that thing.
No, it was very, very informative. Very informative.
Wonderful. I am so delighted. So tell me any questions so far? General discussions. There are many other experts who are better than me on this thread. Anyone wants to add anything? Compliment. The floor is completely open as long as people want. I'm done with my part.
Well, Sudhir, it was excellent.
Sorry.
It was excellent, I said.
Thank you. Let me go back to the video mode because I am not able to see anyone. One second. Now there you are. I am now able to see.
I think now everyone can switch on their video so that we can see each other face also.
Fantastic.
Sir, you can stop sharing.
Oh yeah, okay. Let me do that.
Also, you can close the recording.
Yeah, sure.
Is the sharing on?
Okay, I'm stopping the recording.